Yes, I was aware it wasn't working. It should be working, and it works so effectively that I really can't even talk in a normal voice because it's very loud in this room. Okay? Yeah? I'll remember to smile. You might get a picture taken in the next few days. I think it's 2 o'clock, so we can begin. It looks like we have about, oh, perfect, 15 or so people online and 30, 35 people in the room, so welcome. This is obviously ICTP-SAIFR. This is a modeling pandemic course. If you're not here for the modeling pandemic course, you're probably not in the right place. I'm Joshua Weitz, faculty of the University of Maryland. I just flew in this morning. I was here at 9 a.m., so I beat most of the traffic. I've been here a few times in the past and delighted to be back. This week, you're going to be hearing and interacting with faculty both from here in Brazil and from abroad, and we have 2 of the faculty members here. Roberto, do you want to stand up and introduce yourself? Or?
Well, I'm Roberto Krenkel. I'm faculty of the...
It's okay. And there's a mic. I think you have to, yeah, there's even a mic.
Hello. So my name is Roberto Krenkel. I'm from the Institute of Theoretical Physics here in São Paulo, and working also on epidemic modeling.
And we have Ana Bento also just arrived.
Hi, everyone. My name is Ana Bento. I'm an infectious disease modeler, and I'm the science director at Rockefeller Foundation and adjunct professor at University of Maryland as well.
Great. We can turn that off. And we have also Renato Coutinho, who's local. Unfortunately, he is not feeling so well, and you can, in the theme of this course, maybe hazard a guess. We hope to have him available virtually. He was meant to be here in person. That may not be possible, so we're going to work through that later today, I just learned, so we'll try to sort that out as well. So again, this course is going to run today through Thursday. It's a mini course, so we have a few days on epidemic modeling for pandemic preparedness and prevention. What I wanted to do even before my lecture today is just to get you all oriented a little bit about what's to come, what to expect, how you can make the most out of the next few days, and that applies both for the people obviously in here as well as for those who are joining virtually. And I'll mention a few things in which I think the in-person experience will probably get more out of it. So if you're listening online and you can make it in for certain sections, I would strongly recommend that as well. Okay, so we have a series of lectures and hands-on components. And I just want to walk you through so you know what you're getting yourself into for the week. Today we're here on, obviously, Monday. I'm going to be giving this first lecture, which is meant almost as what is called in concert terms an overture. I'm going to try to introduce you, broadly speaking, to themes that appear in epidemic modeling in the context of an ongoing epidemic. And I will use COVID-19, some of our work, community's work, as a way to motivate things. Hopefully that will also motivate Roberto's lecture on a crash course for epidemics. You know, the folks who applied for this program come from very different backgrounds. And I can't see what everyone is doing online, but just as a show of hands, who here comes from more of a life sciences background? Public health or life sciences background? Okay. Who here comes from a mathematics or physics background? Okay, so about maybe 2/3, 1/3, and I don't know what's going on online. That may also help Roberto in terms of some of the techniques. So people will have different exposure in terms of technical background and maybe different exposure in terms of some of the epidemic terms. We're going to try to cover both. There may be elements at which some of you wish the math would go faster and sometimes you wish it would go slower. So maybe everyone will become equally dissatisfied in the next few days. Keep in mind there will be opportunities, and again, this is a mini course. We can't do a full semester's worth of materials. Our hope is that you're getting links in and hooks into material that could entice you to keep learning more, right? So for those on the math physical side where you're used to seeing classes that just start off at here are the equations, we're just going to start from there. We're not going to do it that way. And likewise for the public health bio people who aren't always used to seeing the equations, we are going to show some equations, we're going to walk you through them, and then you're going to have a chance to do some hands-on stuff, and hopefully there'll be new things for everyone. So that's just really setting the stage, right? We're going to try to use today to get oriented, get you all on the same page mentally for what's going to come. And then in Tuesday and Wednesday, hopefully, depending on how Renato is feeling, we wanted to give you some taste of real-world tensions. What happens when you take these very simple models and you put them in the context of an ongoing global pandemic and crisis, and we will try to address a number of themes, including what happens when there are variants, right? Because it's not just the same pathogen that's at the start that is in the middle or even later on. Also questions of how do you deal with dual tensions? You're not only trying to confront a public health epidemic, but there's also an associated socioeconomic problems that need to be addressed. And then you want to intervene. And those interventions can be vaccinations or also obviously non-pharmaceutical interventions, but we're going to talk about vaccination campaigns and how to make them effective. And you'll notice, and hopefully here I can show you, that there's going to be a hands-on component on Tuesday and Wednesday afternoon. And what that means is that each of you should ideally bring a computer loaded with either Python, R, or MATLAB. We're supposed to have a TA for this course. Is that TA in the audience? Ah, there's our TA. Okay, can you say your name? Just shout it. Denise. Okay, Denise is going to be the TA, and that's going to help facilitate things, and we'll try to have faculty in the room walking around. These are meant as tutorials, self-guided tutorials to get you started on the first day with how do you build your own epidemic modeling code, right? What will be called a deterministic model that I'll talk about later. And then the second day, you're going to build a stochastic model of an epidemic. And ideally, by the end of the second day, you'll have both working and you can compare the two, okay? So that is really our goal. It's written in 3 languages. We have the solutions, so if you don't find the solutions, you will be given them, and I'll talk more about that when we get to that point. So that actually, for those online, that's quite important, I think, to be here, because then you have a chance to interact with others. If you can't make it, then probably what should happen on these chats, we'll try to work with the IT folks, is to create little breakout rooms or at least have some work together. So if you can't make it in, and I get it, there are many reasons why you might not be able to make it, at least you should try to talk to someone who's programming in the same language and maybe even speaking the same language, but that's okay. We're going to conduct this in English. And then the last part, we're going to look a little bit towards the future in terms of challenges. I will give probably a more technical talk just using the Blackboard on Thursday morning, having to deal with questions of heterogeneity. How do you really move outside the scope of these simple models in a deeper sense? And then we'll hear again from Roberto on real-time modeling of pandemics, really in the face of uncertainty. Right? And this is a hallmark of you're dealing with an epidemic which you don't know everything. So how do you deal with that? And Anna will close us off on Thursday with some thoughts on and a lecture on surveillance and information seeking, and also how do we prevent future pandemics. And she won't give you all the answers, but she hopefully will give you a sense of what's at stake and what's to come. Okay, any questions logistically? Each one of these lectures is meant to be about an hour and a half. We're supposed to reserve some time for questions at the end, but I think all of us would welcome questions during the lecture. And again, it's going to be a little bit hard, but we'll try to trade off, and in the chat, if you have questions online, you can try to put them there. If you're in the room, raise your hand. We have these mics. What I will just do, and I'll ask the lecturers to, is just repeat the question. That way we don't have to waste time bringing you the mic. Just yell out the question, and then I'll repeat it so everyone can hear it. Okay? There's a break between each of the lectures, and then I guess the only other thing to note is there is a separate colloquium. Because I'm here, they're making me do a lot of work. Thank you, Nathan. So I'm giving a totally different colloquium, not on epidemics, but on our other work on viral ecology. You're more than welcome to attend. If you need a break, you can take a break too. It's not an official part of the course. You're all welcome and invited to attend, and that'll be Wednesday afternoon. Okay, I think I've done all the logistics. And there are restrooms outside, and you can find them. They're on all the levels. And there's a little coffee room too. Okay, so now you're oriented. Good. Okay, so part of the reason I think why you're here, why we as the lecturers are here, is that in early 2020, and in fact the last time I was here in person was probably a few weeks before society changed in December 2019 for a course. And this emergent epidemic, then global pandemic, transformed every aspect of society, right? So in some sense, this is not just a disease that you're reading about, unfortunately, in a textbook that happened far away, that could be severe, like Ebola virus disease, a severe outbreak, though for the most part highly localized, for example, in small villages, or even the largest one, the 2014-16 West Africa EVD outbreak, was still localized in the sense of being constrained mostly to a few countries. This was a global pandemic, and part of what the epidemic modeling community tried to do was to enter in this period of uncertainty and provide some information about how bad things could get, what steps were possible to make it less bad. I'm not saying it was all successful. Trying to figure out what were the high-impact interventions and what kind of impact they could provide, while also buying time for the progression, if it were possible, of vaccines, which truly radically were able to come into the public use within a rapid amount of time, I mean, outstripping almost any other development process before. Right? This particular image and my talk today will be much more through the valence of the U.S. situation, which I know better. Others here are going to talk more about things that are relevant in Brazil. And so if there are aspects here where you say, oh, what was the comparable in Brazil? I don't have all those numbers at the top of my head, but thankfully my colleagues probably will and probably will address them. But I think some of the messages, for better or for worse, are a bit universal. And some of the experiences in particular between Brazil and the U.S. are, again, for better or for worse, unfortunately a bit comparable. This image was meant to be a heat map of the risk that one or more individuals in a small group, I think about 50 individuals, may have COVID-19. And on top of that, this was this quantitative risk map, which I'll get to. We tried to overlay the motivation for sharing this information. Right? Why people might want to wear masks, why people need to protect those who work in the healthcare industry. So we're trying to prioritize with this message of going beyond just equations and models and numbers and trying to reach many people. And I will try to make that one of the emphasis points of my lecture today. All right, so that we're not just, even though the mechanism by which I'm going to talk about epidemics today will largely be mathematical and modeling, and that will be a theme throughout the week, we have to keep in mind there's a community we're trying to reach and we have to communicate to that community. Okay, so again, these are the themes that you're going to get at in this week. There will be mathematical modeling blended with epidemic realism. We're trying to focus on high-impact interventions and outcomes and trying to give you a taste of what people do in the midst of an epidemic, right? People who often are working in the context of academic centers, but then tried to bridge this real-world gap. And finally, this is at least going to be a taste of hands-on work, meaning you can do it. And I know people here come from very different coding backgrounds. Nonetheless, I'm going to encourage you to make sure you have your own computer and you're typing your own code. Right? You're going to get much more out of it than looking at someone else, because I'm not going to grade and see how great that code is. So the more time you spend on trying to figure it out yourself rather than looking right at the answers or looking at someone else's code, the better off you'll be. Okay. So today I'm going to talk, technically the title was Epidemic Modeling Through the Lens of COVID-19. I'm going to try to use a particular word, this word asymptomatic, as a means to motivate the way that I'm going to explain epidemics, how theoretically they should unfold, but actually in practice how this one unfolded. It doesn't mean that that's going to be universal, because some diseases don't have such a strong asymptomatic route, but COVID-19 did. And again, I'm going to use the word asymptomatic not to mean that it's totally devoid of any particular symptoms, but they're certainly sufficiently mild, subclinical, or in some cases no one would recognize them as a distinguishable symptom. Nonetheless, people can still infect others, and there's a consequence to that. Okay, so that's what I'm going to try to go after today, and hopefully that sets the tone for other lectures to come. And before I do, I also have to recognize this work, and we ended up collaborating with many folks, is supported by a large number of different organizations at different times, and sometimes for reasons unrelated whatever to the pandemic, and we told program officers that we were just going to have to work on this for a couple years. Right? And it's also with a large number of folks, and I'm happy to share at the end papers. Right now we haven't posted anything online, but we will post information. And just so you all know, these are being recorded for the speakers as well. The talks are being recorded, and they'll be available back to you all And there will be some handouts that will help give you some more context that you can read afterwards. So the first slide I want to show is this one. And I don't know does anyone recognize or have seen this image before or can make a informed guess as to which period it might be from? It has something to do with an epidemic. Plague, is that what you're saying? Like Black Death, plague, and so on? Right. So these are images taken from a period which has to do with a plague year, so Black Death and plague. And there's a famous book called a journal, Peste Bubonica, right, exactly. And I don't speak Portuguese, so I speak other languages other than English, but no Portuguese. So when I try to speak Portuguese, I've learned I speak in Spanish and then I make up Italian words. So none of it makes any sense because I don't speak Italian. So I will try, if you write things in Portuguese, I will only half understand them. So this is a quote from Daniel Defoe's beautiful book, A Journal of the Plague Year, which tries to go through the experience of individuals, and it's meant to be both true and not true at the same time. It gives you a sense of what was going on when plague spread. And there's a particular quote that I wanted to share with you all because I think it's quite prescient. And it's written in this old English style, which is not always easy to read. So I'll try to emphasize the important parts. It's a remark for posterity. And the important piece you should take away is it says, concerning the manner of peoples infecting one another, right? So there's some transmission. Namely, that it was not the sick people only from whom the plague was received. In other words, it wasn't just people who were outwardly sick who infected others, but others that were sound, the well, what I'm calling asymptomatic. These were the dangerous people. These were the people of whom the well people ought to have been afraid, but on the other side, it was impossible to know them. Right? And so this idea that somehow a disease from which could be deadly, could be fatal, but could be transmitted by people who seem outwardly, at least for the moment, okay, is one that is hundreds of years old. Right? A few months before 2020 began, I teach a yearly course called Foundations of Quantitative Biosciences, and we have a module on epidemics. And this is, again, maybe too much detail. It was from fall 2019. Many of us who work in this space have already been thinking about what happens when you have diseases that are mixed with feedback, with behavior. And I'll just give you an example, if you can see it up here. This is, for those of you who know what models look like, it's some kind of model. The most important feature here is there's this little function. And it was meant to be an example of a disease like SARS that had a respiratory transmission. Again, this is a homework problem. And you were supposed to estimate something about it, but then, given public health campaigns, individuals start to wear masks, which reduce spread to virtually zero, however compliance scales with disease incidence. In other words, people don't actually want to wear the mask, or only wear the mask when things seem really bad. And the whole problem was about what happens and how bad things were going to be. So for a number of us working in this interface between behavior and disease, unfortunately, we got busy really fast because this is precisely the intersection in which many things happen, right? So although this is an emerging infectious disease, many of the principles that we could think about to use to try to model or forecast what could happen in the absence of interventions, or even try to predict some of the benefits of interventions, were in place in advance. Okay. So I want to get everyone to move back in time a little bit to get oriented with respect to where things were, and then I will move forward in time as I try to explain some of these principles. Okay. So in early 2020, you probably remember, and people remember differently. Sometimes our memories are not always trustworthy with respect to timing, but at some point many of you became aware that there was this emerging infectious disease out of Wuhan. There was a cluster of pneumonia-like illnesses, and Wuhan region became closed, and the US at least, the first case was found in Washington State in late January 2020. And after that, there were case surges in northern Italy and Iran, and it was clear that this wasn't something that had been confined effectively in China, right? there was an awareness this was somehow far away, but you started to see clusters popping up, and then the clusters no longer became clusters, became widespread outbreaks. Was there a question in the back already? They're taking up, let's see if I can get rid of those notices. I didn't even make those notices. Did that go away? Here, let me go over this one. There are many screens here, because you look how many pieces of technology I'm wearing. So who knows, did that go away? Is that better? Okay, it was on the other screen controlling my screen. Yeah, okay, fine. Good. So there was, rapidly speaking, emergence of cases that had obviously traversed borders, despite the efforts of people to identify people at borders, which goes back to this notion of well people who are exposed, maybe incubating, and going to be infectious or asymptotically infectious already, right, but not showing outwardly signs of symptoms. And now I have to see if I lost this button in the process of clicking those buttons. I think somehow now I have to get back here, and now I'm back. Good. So in February 2020, what we tried to do, at least at the university I was based, is try to highlight some of the potential threats posed by this virus. This was, again, early February 2020. And I talked a little bit about potential spread. And one colleague, Trevor Bedford, whose name you may hear, was one of the first to identify the emergence of this outbreak and work to also, with others, identify vaccine targets. He's at Fred Hutch in Washington on viral evolution. And Phil Santangelo was already working on vaccines. I mean, at this point, already people had identified potential candidates for what they thought would be the good target, the spike protein. Right? So very early on, there was already work being done. And one of the things that worried us was that if you had a respiratory illness that could infect many individuals like SARS-1 could, and it could transmit from people who potentially were asymptomatic, then large groups pose many sorts of problems. In the US, at least, we had something called March Madness. If you like basketball, it's this big college basketball game where on the order of 70,000 people come to watch the finals, and they were all supposed to come to one particular place. And obviously, when you have many people together, you don't know who you are sitting next to, so you have many more potential contacts. It's very hard to do contact tracing. So all the things that you would like to do become a lot harder. And we tried to advocate against this, and eventually the CDC, by about mid-March, tried to restrict group sizes to 50, and then after that, it became even smaller as there were stay-at-home orders. So rapidly, this became the emergence of something far away, localized outbreaks that still seem maybe far, to societal changes in almost every part of the globe. Okay? But yet, at the same point that this was happening, that scientists were trying to explain why and how this could spread so rapidly, there were other models that were predicting, and this is from mid-April in the United States, that COVID would be done by the summer. Okay? And I don't know if you're aware of these models or if similar models came out in Brazil, but here's the time of the prediction. This is mid-April 2020. And you can see that there's this prior data of deaths per day, which in the US had risen to 2,000 fatalities in a day due to COVID by mid-April. Right? And here, by early June, there would be 0 cases and 0 fatalities. The other notable point here is that this shaded region are the error bars. Okay? So I just want to pose the question, do you notice anything unusual about this prediction that should give you caution? And just for those of you, I'm not cherry picking a small group. This was the leading, in terms of media coverage in the United States, the leading epidemic modeling group. It's called the Institute for Health Metrics and Evaluation, funded by the Gates Foundation, University of Washington. And their predictions did get better, but I want to just talk about this one here. Does anyone recognize or notice anything that strikes you as odd for any reason? But no, not the professors. Yes. The error is highest in the closest time. Yes, so that's an unusual feature. Thank you for suggesting this. If you notice here, at the day the prediction is made, there's the most uncertainty, but the uncertainty disappears. And there's an old saying that predictions are hard to make, especially about the future. So here we have the opposite, right? So you have the most uncertainty right now and the least uncertainty in the future, right? So that seems an unusual facet of this prediction. Anything else? So whether it looks linear, it almost takes maybe just a little bit longer, but here we have a disease that pops from 0 to peak in about a month, and almost the same amount of time it's gone away. So it's nearly symmetric. Maybe it's a little bit longer on the back end, but that seems also unusual. Okay? So those are two good features. Certainly this uncertainty feature is one that should concern you, even if you don't have a background in modeling. Why is there so much uncertainty? Why wouldn't you expect that tomorrow would be basically like today, right? Making a nowcast, if you're ever in doubt what you should predict for right now, it's probably right now, right? So there's not likely to be that much uncertainty, especially since the fatalities are due to people who are hospitalized, and those hospitals have already been infected, so it's not expected to have some radical jump from one day to the next. In a week or 2 weeks from now, things could get very different, right? So there are many indications that this had some problems. This wasn't the only model that made such a prediction. This is another White House model using an Excel spreadsheet. It was called the cubic model because it used a third-degree polynomial to make a fit. And although that doesn't sound very sensible, it was about as sensible as the model I just showed you. Again, all of these things are predicting that it would disappear. And what you can see is that here's the first prediction in March. It goes away. And then they update it, goes away. Update it again, goes away. So they keep updating the model, pushing forward when it goes away, but something fundamental is wrong here, right? The mechanism underlying these predictions isn't changing, just the data keeps updating because it hasn't gone away yet, right? Of course, what really happened is that there were, in some cases, and this is a regional map of the United States broken into 4 different regions, you had some places where there were declines. I was in the South, in which the summer involved a significant surge. Right, the Northeast, there was a decline, but there certainly was no decline in fatalities and certainly no disappearance of COVID, neither in the US nor in other places in this short a time frame. Right, so this was way off very early and it kept being wrong. So what were they doing behind the scenes? What they were doing actually goes back to a notion by William Farr, which is called Farr's Law, and this is not to criticize William Farr. He can't fight back at this point, but he did amazing things, but we're using an idea that's over 175 years old inappropriately. His idea and his observation, which was really an empirical one, is that he was looking at smallpox outbreaks in England and noticed they happened to have a symmetric-like progression. Okay? Not quite linear, but in other words, he saw cases go up 10, 15, 20, 30, 50, 80, or 90, and then go down 50, 30, 20, 15, 10, and then they would disappear in a community. And he noticed this symmetry, and because of this symmetry, found that you could make some predictions about how long, empirically at least, a smallpox outbreak might last. And this idea became revived in one of the most prominent cases in terms of projecting another emerging infectious disease, HIV/AIDS. And this was done in the late 80s, early 1990s, where if you notice, these are on the y-axis, the number of cases, 1,000, year of diagnosis. And it's starting, do you notice there's like a little bit of an inflection down? So if you believe that diseases must go up and down symmetrically and follow Farr's law, then maybe this early downturn, then something that looks maybe purely exponential, could be an indication that it's going to go away, and that's what folks did. They ended up making this prediction that the number of cases would basically drop to 0 by 1995. Obviously, that is not the case, right? This is the perils of trying to predict something way off into the future based on small changes. And again, this is not a mechanistic model of how many people could be infected. This is an empirical fit to a particular shape of a curve. Obviously not the case, and it was very far off. Here we have 25,000 by 1995. It exceeded 75,000. It's off the scale, right? And that's a story for a different day. What was inside this IHME model? It was something like Farr's law. They used something called the error function, the ERF function, which is essentially a cumulative distribution, which has a particular functional form. And what that means is that they think that the number of cases is eventually going to saturate, and so if you take any kind of PDF, you fit some curve, and the reason, therefore, why you have no uncertainty at the end is because over time, eventually you've saturated your curve and you're done. And so that's why you have all this uncertainty in the beginning and it goes down to very little at the end. And you just keep updating it based on whatever the model data fit is. So your best fit empirical function, but the function forces you to get to essentially zero because the accumulation of cases stops accumulating. And that's also why the uncertainty goes away. Right? There's no uncertainty anymore. It's built into the model. Right? So we can and we should do better than that. In other words, this kind of model is essentially Farr's law returned, which is okay in certain cases, but as obviously was shown in the HIV/AIDS example, not appropriate, and it was certainly not appropriate. And people knew it wasn't appropriate for SARS-CoV-2, COVID-19, because what was the principle to say that there weren't any people left to be infected? What is going to stop this emerging infectious disease that's respiratory, that clearly can infect people very rapidly, from continuing to infect more? Okay? So what I'm going to try to do in my next 45 minutes to an hour, and I will get through what I'll get through, is to try to go through three major concepts. First of all, that COVID wasn't just kind of seasonal flu, it had a severe component to it, but I'm going to try to explain some of the basics of how we describe epidemics in terms of mechanistic interactions. I'm going to try to talk about models of asymptomatic transmission and how they can even worsen pandemic severity. So paradoxically, things that aren't as bad for the individual could be worse for the population as a whole. And then, if I have time, I'll get into what does it take to build model-driven tools to prevent future pandemics. And again, I'll see how far I get through. I have another lecture on Thursday. If I don't get through all the materials, I'll wrap up some of this as well, especially on the tool side, and do some of the heterogeneity. Right? So my hope is that I'm going to give you all a sort of an overture version. We're going to get the crash course, but some of the key ideas that go into epidemic model building that are not just curve fits. Okay? Any questions at this stage? Okay. So, in thinking about an emerging epidemic, I'm going to try to explain two concepts which I'm sure, by this point, most of you probably should know. This notion of R0, the basic reproduction number, the number of new infections caused by a single infectious individual in an otherwise susceptible population, and then something called either the case fatality rate or the infection fatality rate, and they're not the same. In both cases, you're trying to divide the number of fatalities caused by this disease by something. In the case fatality rate, it's the number of cases, those which are identified, maybe because you've tested, you felt sick, you went to a doctor. The infection fatality rate, you're dividing by the total number of infections, which could be much larger than the number of cases, precisely because people were asymptomatic, not enough testing, it was subclinical, not diagnosed. Okay? So the thing that you typically observe is the case fatality rate, because you've measured a case and you know the outcome. And although there can be things like excess mortality, the thing that's usually far more in excess are the infections relative to cases. Likewise, this basic reproduction number is also not directly observed. You tend to see the accumulation of cases and you're trying to figure out the mechanism by which that happens. So at the beginning, we weren't sure about either. We thought that somehow the basic reproduction number was about 3, and it wasn't quite clear what the case fatality rate was vis-a-vis the infection fatality rate, because the case fatality might be even 2 or 4%, but that was not the same as the infection fatality rate. Maybe it was much lower, right? And I'll talk about the consequences of that in a moment. Okay, so how do we actually start to think about what might happen? Well, when we start to treat individuals in terms of categories, that begins a process by which we can start to build a model. Taking a population and considering them in terms of whether or not they're susceptible. At the beginning of the COVID-19 outbreak, we can think that we were basically all immunologically naive. It doesn't mean that we're all going to have the same outcome, but vulnerable to infection. And you can imagine dividing up individuals just based on whether or not they're susceptible, infectious, or maybe recovered. And I'm just going to, irrespective of where they are, imagine they're in this kind of big category and divide people up that way. And if I do, I can have something called a non-spatial or mean field model. I could also try to imagine that there's a region and do the same thing in that region. Right? So I'm going to treat Sao Paulo different than Rio, or the Southeast different than the Northeast. I'm going to try to divide people up in space first, and then within those spatial domains, I'm not going to go and resolve things to so much detail, and I'll still keep track of who's infectious, susceptible, and recovered. Or I might do something and get to the level of individuals, right? Or even some notion of continuous space and increase my granularity. And there are benefits to doing all these kinds of models, and you'll hear about some of them this week. Again, it's a mini course. We can only do so much, right? In the first category is something called ordinary differential equations. The second mixes both network models and metapopulation models, and you get into notions of PDEs as well. So there's a kind of different toolboxes that you might use to try to treat these. The principles, though, if we're trying to communicate the principles, are often best done here on the left side, right? Just trying to explain some of the basic processes, and that's, I think, what we're starting with today. I don't think you're going to go beyond ODE models today. Maybe, yeah, I didn't think so. Okay. Later in the week, I will talk a little bit about PDEs, and so we'll see how that goes on Thursday. We'll see, but it'll be purposeful PDEs, not just PDEs for the heck of it. Hopefully we'll get the essence. Even if you're not used to analyzing partial differential equations, we'll still get the gestalt of it forward. Okay. And of course, depending on which mode of transmission, this also makes a difference, right? So whether or not something is respiratory, something is due to contact, environmental, or some vector-borne illness. And again, each one of these kinds of disease categories brings with it new questions for the modeler in trying to link models and data together, right? So I'm going to focus in this talk on building these non-spatial models in which one individual may infect many others, and not going to worry about space for the moment. Right? So I'm not going to worry about a vector-borne route or an environmental route or contact-based route, but rather some way in which one individual can infect others, and I'm going to differentiate people as to whether they're susceptible, infectious, and recovered, and take it from there. Okay? Good. And I think I said that now twice. So now what am I going to do in this first simplest kind of model? I'm going to talk about individuals who are S susceptible, I infectious, R recovered or removed, and we'll focus just on the recovered category for now. Which means that I take a population of individuals and I'm going to categorize them based on whether or not they're in this S, I, or R category. And I'm going to assume that there are really only two processes I need to worry about to start: whether or not someone goes from the S to the I class due to infection. And for that to happen, we have to have a contact between an I individual and an S individual. And we're going to assume, and hopefully this will be reviewed a little bit later, that individuals have a certain number of contacts, a probability of which lead to infection. And so I'm going to aggregate both those terms in terms of beta, right, as this attack rate of the disease. I'm also going to assume that people who are infectious for an average period TI, right, the time of infectiousness, and therefore I can think of them as individuals who are going to recover at a rate gamma, by definition, 1 over TI. So I can either use the rate gamma, which is units 1 over time, or this time, TI. And that's the only two processes I'm going to worry about for now. Okay? And the name of the game here is to look into the change in the number of S individuals, I individuals, and R individuals, noting that I'm just moving them between categories, if I'm not worried about fatalities for now, such that S plus I plus R is equal to the total size of the population at interest. Right? So that's going to be conserved. So if I have 3 variables, and one of which is conserved, I only have to really worry about 2. Because if I know those 2, I know how many people in the third by just subtracting from the total of individuals. So here I've written what will be your first ordinary differential equation in this course. And it would help me, just because then maybe in the interim we can see how much we want to fill in the gaps. And I have some lecture notes that explains how we derive these things and what they mean. Who here has seen ODEs before in your experience? Who has vaguely seen them? I won't say if you've never seen them. Vaguely seen them. It's been a long time. It's been a long time. Okay. Okay. So a few people, it's been a long time. That's okay. But most of you have seen this before. If it's been a long time, during the break, just come chat with me or with Roberto, and we can try to fill in some of those gaps. The key thing to take away here, and if you come from a biology background, you often think of an update rule. What's the thing at the next time, right? Which is a way of saying in your mind, like, what is S of t plus 1? What's the value at the next time, at the next generation, at the next hour? These left-hand sides are the rate of change. In order for me to figure out what happens in the next time, for example, if I'm running at 2 miles an hour, that's not really running, that's walking, 10 miles an hour, I'm really running, right? No, I'm in Brazil. 15 kilometers an hour, right? Now I'm really going somewhere in metric space. So I'm running, and I want to know how far I am 1 hour from now, right? Then I just take that speed, multiply by time, and I get my position at the next moment. I don't want to go ahead that far in an epidemic model because the system is updating. But you can think of this in the same way as this is the rate of change of susceptibles, the rate of change of infectious individuals, and the rate of change of recovered individuals. And here you can see that susceptible individuals will decrease. Why? Because they're getting infected. And in this model, they're getting infected at rate beta, which we can think of as the number of contacts per time times the probability that someone's infected given the contact. And in this case, I could put actually divide and on the other side, we have I infectious individuals, but they interact with people, only S of N whom are susceptible, right? And so as S and I change, this update is also going to change. We need both infected individuals and susceptible individuals for there to be new infections. I mean, it seems obvious, but this is why this is a product of S and I and not somehow a function of S and I alone, right? Just as a side note, if this were something like cholera or even Shigella, there can be things in the environment, so you might not need an infectious individual to become infected. There could be environmental reservoirs, and so the models can look different. And there are different consequences to that. These susceptible individuals flow into the infectious category here. You see these are the same, just with the minus and the plus sign. And here we have infectious individuals then recovering at a rate 1 over TI. And they become recovered. This is each one of these arrows here in and out represents a new term in our differential equations. And they balance in this case because we're just moving the designated category of susceptible infections recovered. Okay. So what do we expect to happen? And again, keep in mind that these things add to 0, so we don't change the total number, as I've already said. Right? You see those terms just cancel out. We're interested in the case near the beginning, when nearly everyone is susceptible. And if you know something, or you read the news, or you did any work in the space, you know that this magical number R naught will tell you whether or not you expect on average this disease to increase or not. When it's greater than 1, it increases. It's less than 1, it should decrease. But let's see why. Okay. And if it increases, you also expect something like this to happen, where you have this epidemic, it goes up and down. I mean, we almost look like we're in Farr's law category, so maybe IHME wasn't so wrong. And here we have the cumulative number of recovered people, susceptible individuals. At the end, the epidemic goes away. We add these two things together. We get 1. And notably, you always have some susceptible people left at the end of the epidemic, in theory. Okay? So these are the characteristics that I think most of you are familiar with, right? That you have this notion of a critical number, this basic reproduction number, that if it exceeds 1, you get an outbreak. If there's an outbreak, you have this characteristic epidemic curve where things go up and down, and we're left with people who've been infected, but not everyone has been infected, even if R naught is very high. Okay. So let's go back to this dynamical equations for the infectious individuals. For those of you who have taken more advanced classes in nonlinear differential equations, you could linearize this and kind of do your own thing. I'm going to give you the intuition. It ends up in the same place. Okay? I'm going to look, in fact, at the infected subsystem, for those of you familiar with that term. But for everyone else, we're just going to look at the number of infectious individuals. And you see, this is the equation where you have the balance of new infections and recoveries. But near the beginning, everyone is susceptible, more or less. So this S over N is 1, and I can rewrite DI/dt as approximately the number of infectious individuals times some factor, right? And this factor has to have units 1 over time, right? And you can see here I have beta, it would just be beta minus 1 over ti, but I've written it in a different way by pulling the ti on the bottom. These are the same as beta times ti minus 1 over ti, which means the sign of this term depends on the relative magnitude of the product of beta times ti, the attack rate, the number of new infections per time, times some time over which you're infected, which sounds a lot like the average number of new infections caused by a single infectious individual in an otherwise susceptible population. In other words, this thing here, as you're about to see, is R0. Right? And when R0 is greater than 1, that one individual leads to more than one infection, which means the disease keeps growing exponentially. If it's less than 1, it will decrease potentially exponentially. Okay, so you see I've boxed it there. That's R0. And it emerges in this sort of linearization at the very start. Are you seeing, is this going to grow exponentially? Depends on what happens at this individual level. So we have an individual notion of explosive growth, which is what this R0 is. But you'll also note that there's a population notion of explosive growth, which is what you measure. Right? This you don't know, the thing I just boxed. This is what you measure, because you can measure the number of new cases per time. That's the observable. The other thing you want to know, and the reason why the theorists want to know it, is it's going to tell you things, as I'll show you in a moment, about potentially final sizes and also what you need to do to stop the outbreak. But in fact, the speed at which cases grow, because at the end, DI/dt is I times some number, means that we have a very simple exponential equation, right? You probably all remember dn/dt is Rn, which means n of t is e to the rt. Same idea here. It's going to grow exponentially, where the speed is the difference between beta minus gamma, transmission rate minus recovery rate. And that's what you're observing. And it's mediated, the one thing that we want to know, this R0, and the thing we observe, the speed, is mediated by what's called the mean generation interval, the average time it takes between the infector and the infected. And there's, in fact, a whole distribution, but we're only going to worry about this mean here for now. Okay, got it. Now, since you all know everything there is to know now about R0 and its relationship, I'm going to give you a few examples, then take a little poll. Here I have a synthetic example of an outbreak that starts near 0 cases, and here we see this is the prevalence, the number of infected at a certain time, which is different than the incidence, this DI/dt, at least in terms of the new infections per time, technically beta Si over n. And you see that it's growing exponentially. I've added some noise, and here I've pre-calculated R0 as 1.5. So R0 is 1.5, and here's the outbreak. And now I've constructed another outbreak with R0 as 2, and another where R0 is 2.5. Does anyone notice something unusual about these 3 curves and 3 synthetic outbreaks? The what? The colors are different, yes? Which is another way of saying, a funny way of saying the lines are the same. Okay. But I was told, I thought that R0 is bigger, it's a worse outbreak. Why is this possible? Why are they, and I can assure you I did the calculation correct. The R0 is in fact 1.52 and 2.5. So what's different here? We have to look forward in time to see the consequence, but you can already see another consequence of this funny feature. If I were now to look forward over the equivalent of about 3.5, 4 years, you can see now we get a divergence in the long-term outcomes. Those with a higher value of R0 have a higher peak prevalence and take a longer time to go away and ultimately infect more people than those that a lower value of R0. But the initial speed can be the same. And that's tricky because you don't know the R0 at the beginning. You measure the speed and you're trying to go backwards. And when you're not sure about the generation interval and the transmission rate at the same time, you have an identifiability problem. So there's an uncertainty at the very start if you're trying to infer R naught from little r. Okay? So again, I already showed you the equation. You can see you have different combinations of beta and Ti that could yield the same little r with different values of the product. Okay? And I'll leave that to some of you if you want to explore that consequence. So what does this already tell us? That here we have the speed that we measure. We want to figure out R naught, but it may not be possible. Here we have 3 different values of R naught. They all have the same speed. We can't go backwards, right? There's going to be uncertainty in what we infer. But yet, later on, this could lead to quite different sizes because of the fundamental differences in strength. And this is really why many folks in the modeling community were preoccupied with big R and not little r, because of this long-term outcome. Okay? And I think I just said all that. There's an identifiability problem. Many values of R naught can be compatible with little r, so going backwards is hard. And this actually had consequences at the beginning. Okay. Let me try to explain this concept, not just algebraically, but intuitively. Here's an example, and this was out in 2019, before the epidemic emerged. 2 examples in which, if you can see here, the curves look precisely the same, and also all the slides are going to be available too. So take the notes that you want in the moment, but if you miss something, you can get it later. What you can see here, that these are the same weekly incidence curves. On the left is an example where the generation intervals are shorter, meaning each individual is infectious on average for a shorter period, on the right for a longer period. If they're infectious for a shorter period, that means there are more generations to recapitulate the same incidence curves, which means per generation, you're not infecting as many people. Whereas on the right, it's a longer period, and therefore you have to infect more people per generation to recapitulate the same incidence curve, which leads to a rule that constrained upon your observal, you observe an incidence rate, the number of cases going up. Smaller values of the generation interval mean smaller values of R naught, and things that extend the generation interval mean larger values of R naught. Okay? You can see this, if you're still not satisfied, even another way. Here we have R naught 2. In order to get this many, I have to go 1, 2, 3, 4 generations. So when the generations are more rapid, the R naught is smaller, whereas if I want to get to the same number of incidents at the end, if I have a higher value of a longer generation interval, then my R naught is also higher. Same idea. Okay? Again, this is an old schematic. This paper is by Park et al. Epidemics 2019. Okay, so we have this link between speed that we measure, the strength we want to observe, and this generation interval we might not be sure about. And this also helps to interpret headlines. So here's one: COVID-19 might be twice as contagious as we thought, which is unusual, even at the time in April, because we had observed a lot in early cases out of Wuhan to have a sense of how many people were going to be infected. What was really happening is that people were taking the same data, the same case count data, right, but then changing their assumption about intervals. So here we have a growth rate, the growth of the number of cases per day. So let's say we observe something here, which is about kind of a 4-day doubling period approximately of cases. Here's the inferred R naught. Here are different assumptions about intervals. These are technically serial intervals, which I'll explain in a moment, which are different than generation intervals. Just think of them for now as an interval. And what you can see is that if you make an assumption constrained upon what you observe, that the intervals are on average short, then R naught is lower. And if you think the intervals are longer, R naught gets higher. And this headline is basically saying we're now assuming that the intervals are longer. And that means per individual, they have to infect a lot more people. Okay? Early on, when we were trying to figure out the R naught of COVID, people didn't agree upon the assumptions of the generation interval. It also depends on behavior. Yes, you may be infectious, but if you take preventative measures because you're aware of what's going on, then you're effectively changing your generation interval distribution and the mean generation interval. Right? So we have to separate out just what the etiology of the disease is. Are you potentially infectious versus what you're doing? And together that ends up impacting this generation interval distribution. So a lot of the uncertainty early on was really people making different assumptions using the same data, right? And coming to different conclusions off by sometimes very large factors. Okay. So there's that piece of the puzzle. So there's uncertainty at the beginning, so you can see how we might go through this mechanism, but we have another issue, is what if we were missing the vast majority of cases? And this goes back to some of the logic of the IHME model. Yes, we're observing the speed. What happens if for every case that we observe, there were 5-fold as many infections? What happens if there were 10-fold as many? What happens if there were 100-fold as many? Right? So I don't know how many of you know the actual answer to this, but it has consequences. What happens if early on we see that, let's say, 0.5% of the population is infected, and we see severe fatalities on the order of 2,000 per day, but yet for every case that we document, there were 100-fold infections that we hadn't found? What would that have meant? Anyone hazard a guess? What would that have implied? So we're seeing a certain number of cases. It seems bad, but for each case we document, there are 100 more infections that we haven't found that are out there. And those people aren't going to get infected again. What do you think a consequence might be? The disease is severely less fatal than we thought. 100-fold, the CFR and IFR is off by a factor of 100. What else? Let's go through that. Keep going with it. Anyone else want to help? Finishes faster. We're almost done. We've almost used up all of the susceptibles. I told you that the new infections are a product of S and I. So if we deplete the S's really fast, we're almost done. It was terrible, but we're almost done. Okay? Those are the two key things and why this notion becomes very important when there is this asymptomatic route of transmission. Okay. So it's both far more contagious, a lot more people had gotten it, but there are these other kind of double-edged features of the sword. Like it wasn't actually as fatal, and we're almost done. Okay. So how would we figure this out if we're not doing a good job at tracking and documenting cases? One way to go and figure out who has been infected, right? We're trying to figure out who's in the R category, is looking for signals of prior infection, which are antibodies. So individuals who've been infected who you may not have done because they weren't even available, there were problems with the CDC toolkits in the United States, even if people had tests that were potentially out there, weren't enough of them to be tested in the period in which you were infected, and these were at the beginning costly or hard to get or even delayed viral PCR molecular tests. So what I've tried to show here are different arcs of a viral load at the beginning in which you may test positive using, at the beginning, a PCR test and later antigen tests. And then the accumulation of antibodies for which you might test antibody positive but even antigen negative and viral negative, meaning you don't have presence of viral genetic material in your system and you don't have presence of enough antigens, these sort of parts of the viral structure that are looking around that you could see rapidly on one of these rapid test strips, but you see these long-lived antibodies. Okay? And one way to go about might be to sample individuals in the community and try to figure out who has antibodies, and then compare that to how many people you saw test positive using viral tests and look at how big this gap was. In other words, you could look backwards in time, look for documented PCR reports of positives, and this is what happened in the Bay Area in what is called the Santa Clara Serological Study in early April 2020, and then go out and do a community survey and find how many people had antibodies. Right? And I've drawn these pictures here as a means to say you're trying to compare what fraction of the population you think was viral positive versus those that are called seropositive. And now I'm going to stack them hopefully together. And at the time, people thought the underreporting was something like 10%. So 1 out of 10. You're still missing a lot of cases, but that's very different than 1 in 100, right? Or more. If you think that it's not just 1 in 10, but in fact something like 1 in 100, then the population fatality rate is going to go far down. So you have your case fatality, but your infection fatality rate is going to be far lower. They didn't quite use the right term here because I'm just quoting from them. It says a population-wide case fatality rate of 0.05% is lower than seasonal influenza. If that's true, then locking the world down is going to have terrible consequences, and compared us to being afraid, an elephant to being afraid of a house cat. That's why I showed you the house cat. Okay, so this was the premise, and they claim that they found this level of gap between the seropositives and the viral positives. There are many issues with this study about how do you do serosampling in an unbiased way, but the thing that I want to go back to is the point you raise, is that initially if R0 was about 3, each individual infects 3 other people, then eventually we get to the point where we just don't have enough susceptibles around. And that's called, this point, the herd immunity threshold. And that's where I may have infected 3 individuals, but if 2 of those 3 individuals have already been recovered, then I'm only going to infect 1 more individual. And that's a replacement value, right? So if that's true for all the people who are infected, then at the next time step, right, then basically the same number of people are infected, but then there are even fewer people, and eventually the disease starts to decrease, okay? So we might expect this peak in cases corresponds to susceptible depletion. We're running out of susceptibles. And this goes back to how much our underreporting value was. If it was a 1 in 100, we're going to run out of individuals to infect very rapidly. I'm not, in this first lecture, going to derive for you the final size of an outbreak as a function of R0, and I don't know if you're going to do it. Good. Look at us communicating without ever, implicitly communicating. So you will see that later, but I want to give you a preview of it. If you start with the entire population susceptible, and I just want to note that you're going to get the theory for this later today, and you will make this plot yourself this week. This is a phase plane of a trajectory, so I'm showing time implicitly. I'm starting over here, and at the end of the epidemic, I end up somewhere down here where there's no more infectious individuals. The epidemic is over. And my susceptible fraction gets close to 0, but not to 0, as an increasing function of the value of R0. Okay? So if you have a susceptible depletion, I just want to also point, it's going to be where my cases are peaked. I just want to point out here that you can already see this notion of epidemic overshoot, right? Because here is where my cases peak, but clearly I have a lot more cases left to come. And that's because when you're already in the midst of an epidemic, then just because you reach this threshold doesn't mean the disease disappears. It's just now at a replacement value, but there are a lot of people to replace. This was another misunderstanding of what happens when you hit the threshold. The idea was that, oh, somehow it was all going to go away. If I vaccinated people early on, then yes, that can stop outbreaks before they begin. But if they're already in the population, there's no rationale for it to suddenly disappear once you have this susceptible depletion. There's still a lot of susceptibles around. They're just at a replacement value. Okay. And here I've shown it explicitly between this herd immunity threshold, which Roberto will cover, as well as the epidemic overshoot as well. Okay? This is why this notion of trying to get the number of asymptomatic cases was so key. Okay. So this will be revisited later today, and I'll get back to it on Thursday as well. Okay. What actually happened here was something a little bit worse than just not doing your statistics in the best way. There's this other notion of specificity in medical tests, and serological tests are notoriously challenging even with high-quality tests. And I'll let you all think about this for another moment, but if you've ever gotten tested for something, you might want to ask, well, doctor, what's the specificity of this test? And the specificity can sound really good, like 97% or 99%. A 97% specific test means that you could still get 3 false positives in a population where no one has the disease. Even if a 99% specific test means you're going to get 1 false positive per 100 individuals. If you have a low incidence condition, like COVID at the start, where very few people had it, and use a test with a good but still not perfect specificity, what you're going to end up getting is as many false positives as you get true positives, or potentially even more, to the point that you can't distinguish the fact that maybe no one in the sample actually had COVID who had a positive antibody test. It was in the realm of possibility. Okay. So how should we have thought about this disease early on, as most of the people in the community did, not through this IHME model of it going up and down as if we're in the Farr's law version of the universe where people don't react or change or do anything different, it just runs its course, nor should we have thought that somehow we went from an entirely naive population to one in which, because of some vast undercounting of infections versus cases, that we were almost done. It was terrible, but we were almost done. Some of the early models, though they had problems, got the essentials right. In the absence of interventions, these Imperial College models and other models that were more local basically use the following logic, that if you have an R0 of about 2.5, maybe it was 3, you might have 75 to 80% of the population being infected. And if your infection fatality rate was a little bit less than 1% at a population-wide average, it's not true for individuals based on age-stratified values. They're quite different for the young or for the old. You would end up getting something like 2 million fatalities in the United States, right? Or above 1 million in Brazil, or hundreds of thousands in the UK. And unfortunately, that is far closer to the answer than these other models in which say it was all going to go away. Okay. And just to give you some context, this is on a yearly basis, the difference between COVID and influenza deaths. Influenza 2018-19 US versus COVID on an aggregate basis, but per year in 2020-21, 500,000 fatalities, COVID, 27,000 on a typical year. Obviously, it goes up and down. I also want to point out that the risk ratio here in terms of total fatalities for the young, less than 18, is not that different than influenza. That's not to say that's a good thing. You just added another seasonal influenza, and that's bad. It's really for older individuals, particularly much older individuals, where this risk ratio becomes much higher. And I think it's important to point this stuff out just because it is tempting to describe these age differences as not sort of existing. It's neither that it's not seasonal influenza, but for certain age groups, the net aggregate effect was not as severe for other age groups. There really were age-specific differences. Okay. So, I got through part one, and only it took me, an hour or so. But we're just beginning, and I'm trying deliberately to make sure I'm explaining things at a certain pace. Are there any questions? Because I at least want to get through part 2 today and leave some time for questions. Okay, well, let me just keep going. If there are questions on the chat, was there a question? Yeah.
How is the curve in a Chinese city when the Chinese government isolated it?
So the question is, how did the curves look like in Chinese cities when there was severe lockdown? So there were some early papers. I know that there were indications, and most of the early spread went up, and our estimates are from explosive case growth in Wuhan, but then rapidly things got locked down, and they did not continue either to sit in a long plateau, as I will maybe show you later, or through an epidemic case curve that went and reached anywhere the total population. And we know that because, unfortunately, much later on, when China and also Hong Kong reopened very rapidly, and we're still not able to figure out how many total fatalities there were, but then there was explosive case growth then, so the vast majority of people seem to have still been naive despite vaccinations. So clearly this was nothing like an epidemic curve that would have reached, based on the value of R0, it reached nowhere near levels that you would have expected if it had been an unmitigated epidemic. With respect to the shape then, it went for a long period because of tight controls, where basically, for a year or so, people described parts of East Asia as a big success. And again, my contrast for that would be New Zealand and Hong Kong, very similar population sizes. New Zealand's vaccination strategy involved nearly universal vaccination of older people. not true in Hong Kong. They both opened up radically different fatalities because of this difference in vaccination. There were still people exposed, but then unfortunately older individuals hadn't been vaccinated and you had much higher fatality rates. So I can't remember exactly all the curves, but I can assure you that it went nowhere near to saturation, and it was at a suppressed level for much longer. In the US at least, we saw things that were often close to R01 and then exploded up, but there were longer plateaus, which I don't think one saw in China. I don't know if Anna or Roberto want to add anything to that. No, just in relation to anything else you wanted to add about shapes of. Okay. There are some, maybe hear more about Thursday. There's some early papers I can point you to about the impact of mobility restrictions and then how that related to case counts, but I can follow up if you want to see another paper about that. Yep. You're asking, we're looking right now in these models at the number of infected individuals, what would be called the prevalence. Yeah. So I think the question is, what happens when there's potential reinfections? Is that what your question is? Yeah, so you may be thinking about, so the question has to do with reinfections. For COVID, clearly people can get reinfected more than once. It's typically from a different variant because there's variant changes. Right, so we will cover that. Hopefully Renato is going to cover variants, and I don't know if you're going to cover a little bit of models in which there's effectively a loss of immunity, and there are consequences to that. In basic models, that could mean instead of an epidemic, you have something endemic, and you have either a constant level of infections, or depending upon the delay structure, how long it takes you to recover, you can actually get oscillations due to the periodic loss of immunity and the timing of these epidemic outbreaks. And I guess the other thing I could say to that, you might be thinking about something like dengue, in which a second infection can be worse than the first. And I don't know if you're going to talk a little bit about vector-borne models today. I don't think that's going to be covered as much, but certainly severity can be linked in a very different way than it has been for COVID, in which the first exposure seems to have been the worst. Other diseases, second exposures can be worse. I don't know if that helps to. So we're going to have to keep in mind that we can't cover everything here today, but you have an important caveat for those who are not from bio backgrounds, that it's not always the case that the second exposure is going to be milder than the first exposure. Okay. So let me just try then. Ooh, it's already 3:15. I will try to get a few ideas across here, and if not, I'll just continue again on Thursday. Also depends if Renato is not available. I'll just continue tomorrow, which is I can move things around. We are supposed to reserve time for questions too. So are there a lot of questions now, or should I just do at least, can I just try to get through 10 minutes? Because there's some nice pieces here. Let me try to get at least through 10 minutes. Okay. So what I'm going to try to do here in this last bit is talk a little bit more about a somewhat more nuanced model of what happens when you explicitly include asymptomatic infections and transmission. And the issue is that people can feel fine, still transmit, as I already mentioned. Right? This is made a bit troubling and challenging because early on, there were declarations that COVID is not airborne, neither in the colloquial sense or in the technical sense, which has to do with certain cutoffs of filter sizes and so on. But in the colloquial sense, it was always airborne, transmitted through the air, through whether it be a cough or a sneeze, and ultimately people started to realize, and even very early on, through these respiratory droplets that can sit for much longer than 6 feet. And we knew that from various studies. This is a classic image now by Lydia Boriba of MIT. She induced herself to sneeze, used high-speed videos to look at the tracking of respiratory droplets. And they can, because you have this humid group of droplets rather than a ballistic single droplet that just falls to the ground, they can stay in the air for much longer. This is a nice high-speed video. There was empirical evidence, one, this restaurant case where the shaded individual A1, there were different family groups. No other one had any evidence of travel to Wuhan. Nonetheless, all the people who were circled got infected over a much longer distance. There was an air conditioning unit. That wasn't really part of it. There was a choir case in Washington, which is well known. Multiple cases in which you see large impact events over longer distances. And although these were said to be partly special cases, the real issue here is that just being more than 6 feet away is not a guarantee of not being infected, because this is being transmitted through the air. Another issue, another evidence that we knew asymptomatic infection was important is this example of something called a serial interval distribution. This is the time, the serial interval, between when the infector and infectee exhibit symptoms. So I'm infected, Roberto gets infected by me. That we know that because we do some contact tracing and realize that Roberto was never near Wuhan. I came from Wuhan. Roberto gets infected. We're in contact. But he shows symptoms before I do. So you can actually have a negative serial interval. Generation intervals are always positive. Obviously, the time between when I got infected and when I infect him is a positive number. But the person I infect can have symptoms before me. This is quite scary. I mean, this was one of the reasons why people were very nervous. You have a substantial amount of this distribution, which is basically the people you infect are showing symptoms at the same time, effectively, or before the people who infected them. Right? That's very hard to control. It was already too late. Even if they exhibit symptoms later. This doesn't even count people who never really exhibited symptoms, who had mild symptoms. And this was, again, out in early spring 2020. And there are other examples that people kind of CT values that are similar, but I think I'm going to skip that for now and just try to explain this notion of a double-edged sword and get this idea out before the break. Okay. So what is this double-edged sword of asymptomatic transmission? On the x-axis here, I've plotted the fraction of individuals who have asymptomatic mild subclinical infections. On the y-axis, I'm going to have fatalities per case. So if no one is asymptomatic, I'm going to assume that those people have symptoms and some fraction, a CFR, have a fatal case. Whereas over here, if everyone is asymptomatic, I'm going to assume it goes to virtually zero. Right? People with asymptomatic infections are not going to die of this illness. On the other hand, the number of cases or number of infections, I expect to go up because there's just this potential for more and more infection and transmission if I don't know that I have symptoms. And you can see here that there's going to be some tension. What happens for the individual may not be the same as what happens for the population. So what can we do? We can take the SIR model I built before and now say we have susceptible and exposed individuals. They're exposed but not yet infectious. And I'll split them. P is the infectious, but they're asymptomatic. 1 minus P is infectious symptomatic. And only a fraction of the symptomatic people will eventually lead to a fatality. And the rest will become recovered, and all the asymptomatic people will recover. I realize there's also a long COVID literature, and that's a different issue, but I'm going to focus now on these fatal cases. Okay. I'm going to assume that the CFR is about 1%, right? And I'm also going to assume that people who are symptomatic eventually become aware that spreading this to other people is bad and take steps, whether imposed by government agencies or chosen by them, and reduce their contact with other individuals because they self-isolate, they're quarantined, they wear masks, or other reasons by some factor delta. I'm going to assume delta is high. Does everyone understand the rules here? And I'm going to probably also assume that symptomatic people may even affect a few more people than do asymptomatic people. That's not as important, but I'm going to build that in. Okay. And just one last caveat, that a lot of what vaccines are doing are not stopping this, but moving people from the symptomatic to the asymptomatic category. Okay. We can take this model and turn it into a set of differential equations where we have now beta A and beta S are different potentially attack rates for asymptomatic, symptomatic people. You'll notice that the symptomatic attack rate is reduced by a factor of 1 minus delta. So when delta is 1, symptomatic people are perfect in terms of stopping all transmission. When delta is close to 1, they're effective but not perfect. You see the new infections flow into the exposed category, exposed transition to infectiousness at a rate eta. A fraction p become asymptomatic, 1 minus p symptomatic, and then again, this just flows into the recovered class, and we can keep track of total fatalities in the D dot class. Okay? Same idea as before, just a few more categories. The interesting thing here, and I'll just try to ask before, as a function of p, the probability of being asymptomatic, where do you think the worst condition is for the population as the whole, in terms of the total fatalities at the population level? So if I were to draw, I even have this, function P, and I were to try to draw the total number of fatalities. This is 1, this is all asymptomatic. I'm saying words, but I'm not spelling them. Symptomatic. So we go from all symptomatic to all asymptomatic. What's the worst case for the population as a whole? Let's have some hands. Say again? Were you going to say something? Yeah. You have to speak up a little bit louder. Asymptomatic on the right. So you think over here, close to the right side, okay? Close to the left side, okay. In the middle, okay. The question was, where is the peak number of fatalities for the population as a whole? Remember, there's a population model. For the individual, clearly, if everyone has this outcome, each individual is doing fine. Over here, not a good outcome, depending on the disease. But maybe not that many people get infected, which means the total number of fatalities at the population level might not be peaking there. So what I'm going to show you is the outcome. These are for different values of R naught, different values of symptomatic people restricting their transmission near 1 but not close to 1. I want you to see that for reasonable values, the peak fatalities per 100,000 individuals are all in the middle. Because of this double-edged sword. And I'll give you kind of examples of this. And this pops out, and if you want to build by this week, you could build a model just like this, right? It pops out as a function of the fact that you're getting more infections as you go to the right, but each of which is less severe. Okay? The basic reproduction number here is just the contribution from these two routes, and you'll notice that if delta was 1, we only have the asymptomatics doing the transmission, but in that case, no one's going to die, right? Whereas if p were 0, yes, you'd have potentially a higher reproductive number, but if delta is high, if people take restrictions, at some point, you're not even going to have an outbreak, right? So you see the tension that sits between these. Yeah. Okay, so that's so I'm gonna raise a provocative point. I worked on Ebola virus disease models. I worked on COVID-19 models. I was more worried about COVID-19 models and the outbreak that could happen. At an individual level, EVD is awful. 50 to 70% more mortality. There's palliative care. It can be improved a little bit. It's an awful disease. Almost no asymptomatic transmission. Because there's almost no asymptomatic transmission and people are infected, very limited mobility, the people who are infected are often caregivers, public health, individuals who are giving them care, family members, or if they're in a hospital setting that is not an Ebola isolation unit. The total size of those outbreaks is far smaller, even this giant one. So I'm not disagreeing with you, but I'm just pointing out there's a difference between SARS-1 and SARS-CoV-2. And in fact, the difference between SARS-1 and SARS-CoV-2, SARS-1 had almost no pre-symptomatic or asymptomatic transmission. Higher fatality rate, 10 to 12%. I mean, that was very bad for individuals, whereas this is probably 0.5% to 0.8%, depending on population demographics. Yet for the world as a whole, because of this ability to transmit asymptomatically, far more fatalities. And I'm just trying to introduce this tension between the individual and the population, and there is a tension there, right? So it's tricky, and it's also tricky. I think this is one of the reasons why it became hard to stop, because actually the individual, it didn't seem that bad. But for the population as a whole, it was. And I'd say it's even worse because this age specificity also meant that young people knew that actually for them it really wasn't as bad as it was for older people. So there was this same tension even within the disease. I'm happy to talk about this more. It is a tricky topic, and I'm glad that you raised it. So it's my view on it. If we take the same idea here, and we look then at proportion asymptomatic and the number of infections, so this is the proportion infected. Many more people become infected. These things basically all go up. There's a slight decrease there, which we can talk about later. But the fraction of fatalities is peaking here in the middle, right? And these are for different values of steps that symptomatic people do to reduce new infections. If they take no steps, you get rid of this, but people are taking steps. So paradoxically, more asymptomatic transmission is actually worse for the population as a whole. And I think the SARS-1, SARS-CoV-2 case bear that out, as well as these other extreme cases. Okay, and I think I can make this point one last way with this table. If you didn't like those, let me just finish the idea. Here's generations, asymptomatic, 100% asymptomatic spread. You see this disease is doubling or going up by factors of 4 explosively. No symptomatic cases, no fatalities. Many infections, no fatalities. Here's an example in which you're inevitably getting symptomatic case, and yes, there's some fraction of those clusters might lead to a fatality, but you're not getting explosive growth if delta is high. And then it's really the in-between case where I view these asymptomatic individuals as being the catalyst for terminal units in sort of like a branching network where you have these leaves, and these nodes that are symptomatic could lead to a fatality, but it's really the asymptomatic mild cases that are driving new cases. Okay? So this intermediate case becomes ultimately the one that has this highest number, not in terms of infections, but the thing that we're worried about, which is severe outcomes at the population level. And one last thought, and then I'll take questions, and I think we'll have to go to coffee break, and I'll sit around for people with time, which is, if Omicron is less severe, why are deaths rising? The same idea can be applied with this model. If you start with asymptomatic, here's what we think the deceased asymptomatic curve is, and here's new variants. One which is far more asymptomatic, far less severe. If you rerun the model, assuming that everyone who hadn't been infected before could be infected, the issue with this high asymptomatic rate is that many more people become infected in a very short period of time because people are not taking the steps to prevent infection. And when you actually look at these, at least in model land, the daily fatalities in these two cases, you can have severe outbreaks with large numbers of fatalities, even with a milder disease. Okay? So I just want to, again, put this tension out between individual and population level outcomes. And this is something that, again, from the epidemic modeling side, public health side, aren't necessarily always aligned, but we have to keep in mind what is the risk for the population as a whole. And I will now stop there. I clearly do not have time to do part 3. So I'm going to pause. For those of you who are online, you can get your coffee at your home. For those of you who are here, I believe that there's free coffee outside. Restaurant, we're going to start in 30 minutes. And I'm happy to sit around for a few more minutes and take questions. And I can revisit some of this again on Thursday. So thank you. I'm going to stop this button now.